welcome to all in the lecture series of functional analysis. Now in last lecture we see very important lemma, that is the lemma 2.4.1 about the linear combination. Now after that lemma we have to prove the theorem 2.4.2, that is about the completeness. Now the statement of this theorem is every finite dimensional subspace of a norm space X is complete. In particular, we have to show that every finite dimensional norm space is complete. So we start with the finite dimensional norm space, that is capital Y. Let capital Y be any finite dimensional norm space. Capital Y be any finite dimensional norm space, that is dimension of Y, it is equals to n, that is not equals to infinity, that is the dimension of Y. Now here be any finite dimensional norm space, that is dimension of Y equals to n, and therefore n e1 e2 up to so and en, e1 e2 up to so and en be the base for capital Y, be any basis for capital Y. So it is the e1 e2 up to so and en be any basis for capital Y. Therefore for any element small y belongs to capital Y, it is written as the unique linear combination of e1 e2 up to so and en. That is, for any y belongs to capital Y, small y has a unique representation y is equals to alpha 1 e1 plus alpha 2 e2 up to so n plus alpha n en, where alpha 1 alpha 2 up to so n alpha n, they are the scalars. This is about the be any finite dimensional norm space. Here we consider capital Y is finite dimensional norm space, therefore its dimension must be finite, that is not equals to infinity, and as it is finite dimensional, therefore it has the basis e1 e2 up to so n en be any basis for capital Y. As it is the basis for capital Y, that means each element of capital Y must be written as a unique linear combination of e1 e2 up to so n en, and therefore here small y belongs to capital Y, therefore y is written as the linear combination of alpha 1 e1 plus alpha 2 e2 up to so n plus alpha n en. This is about the finite dimensional norm space. Now here we have to show that this finite dimensional norm space capital Y is complete. We will show that capital Y is complete. To show that capital Y is complete, that means we have to show that every Cauchy sequence in Y converges in Y. That is, we have to show that every Cauchy sequence in Y in Y converges in Y. So we start, as here we have to show that every Cauchy sequence in Y converges in Y. So we start with any arbitrary Cauchy sequence in Y, and we have to show that that Cauchy sequence in Y converges in Y. That is, we have to show. Let sequence Ym be any Cauchy sequence in Y. Now here we start with the any arbitrary Cauchy sequence in Y, and we have to show that this Cauchy sequence in Y converges in Y. As it is a Cauchy sequence in Y, that is, it is a sequence in Y, that means here each ym, that is for all m, ym, it is the element of capital Y. Now ym, it is the element of capital Y, and the base for Y is the collection of all E1, E2 up to so and En. It is the basis for Y, and therefore ym belongs to Y implies that ym has a unique linear combination of E1, E2 up to so and En, and therefore ym, it is equals to alpha 1 m E1 plus alpha 2 m E2 up to so n plus alpha n m En, where alpha 1 m, alpha 2 m up to so n alpha n m, these are all the scalars. That means each element ym belongs to Y. It is written as the unique linear combination of E1, E2 up to so n En, and it is true for all m. Now sequence ym, it is a Cauchy sequence in Y. Now here we apply the definition of Cauchy sequence as sequence ym is a Cauchy sequence in Y. Therefore, by definition of the Cauchy sequence, for every epsilon greater than 0, there exists a natural number n such that for all m comma r greater than or equals to capital N, norm of ym minus yr, that is less than epsilon. This is the definition of the Cauchy sequence. Now we are putting the value of ym as well as yr. As here the value of ym, it is equals to the alpha 1 m E1 plus alpha 2 m E2 up to so n plus alpha n m En. This is also written in the summation format. It is equals to summation j is from 1 to n alpha j m ej. This is ym, and now we are putting the value of ym, that is norm of summation j is from 1 to n alpha j m ej. This is the value of ym. In the same way we are putting the value of yr, that is minus summation j is from 1 to n. Now instead of m we are writing r. Alpha j r ej, it is less than epsilon. Again it is true for all m comma r greater than or equals to n. That is norm of summation j is from 1 to n. In bracket we are taking alpha jm minus alpha jr into ej. It is less than epsilon for all m comma r greater than or equals to n. That is norm of summation j is from 1 to n alpha jm minus alpha jr into ej. It is less than epsilon for all m comma r greater than or equals to n. Now here E1, E2 up to so and En is a basis for capital Y. As it is a basis for capital Y, implies that the set E1, E2 up to so and En is a linearly independent set of vectors in a norm space capital Y. As it is a linearly independent set of vectors in a norm space capital Y, and therefore by lemma 2.4.1, that lemma says that for every linearly independent set of vectors, there exists c greater than 0, such that here as in 2.4.1 we have norm of alpha 1 x1 plus alpha 2 x2 up to n plus alpha n xn, it is greater than or equals to c into in bracket mod of alpha 1 plus mod of alpha 2 up to n plus mod of alpha n. In the same way we apply here the lemma 2.4.1. Here we apply the lemma 2.4.1 for the linearly independent set of vectors e1, e2 up to n en, and therefore here by this lemma there exists a number c greater than 0 such that norm of summation j is running from 1 to n. Here the scalars are alpha jm minus alpha jr. J is running from 1 to n, alpha jm minus alpha jr into ej, it is greater than or equals to c in bracket summation j is running from 1 to n mod of alpha jm minus alpha jr. We give it the equation number 2. Now now from the equation 1 and 2 we write from 1 and 2 we get c into summation j is running from 1 to n mod of alpha jm minus alpha jr. It is less than or equals to norm of summation j is from 1 to n alpha jm minus alpha jr into ej. This is the inequality 2, and this is from equation 1. It is less than epsilon when m comma r both are greater than or equals to n, and therefore we are writing here for all m comma r greater than or equals to n. Now combining this inequality we get here, that is c into summation j is from 1 to n mod of alpha jm minus alpha jr, that is less than epsilon for all m comma r greater than or equals to n. Now here this c, it is strictly greater than 0. That means here c, it is not equals to 0, and as it is not equals to 0, so we can divide on both sides by c, and we get here divide on both sides by c, we get summation j is running from 1 to n mod of alpha jm minus alpha jr. It is less than epsilon by c. It is true only for all m comma r greater than or equals to n. That is summation j is from 1 to n mod of alpha jm minus alpha jr, that is less than epsilon by c for all m comma r greater than or equals to n. Now this is the sum. This sum is lesser than epsilon by c, and therefore for each fixed j, j is between 1 to n mod of alpha jm minus alpha jr, that is one of the term of this summation. It is always less than or equals to the whole sum summation j is from 1 to n mod of alpha jm minus alpha jr. This is the summation, and it is one of the term of this summation. Then naturally this term is always lesser than this sum, but this sum, it is strictly lesser than epsilon by c, and it is again true for all m comma r greater than or equals to n. Thus for each fixed j, we get for each fixed j 1 less than or equals to j less than or equals to n, we get mod of alpha jm minus alpha jr. It is less than epsilon by c for all m comma r greater than or equals to n. Now we read this inequality like this. For a given epsilon by c greater than 0, as we know that epsilon it is greater than 0, c is also strictly greater than 0, and therefore epsilon by c it is also greater than 0, and thus we read this inequality like this. For a given epsilon greater than 0, that is for a given epsilon by c greater than 0, there exists a natural number n such that for all m comma r greater than or equals to n, we get mod of alpha jm minus alpha jr. It is less than epsilon by c for each fixed j. This implies that the sequence alpha jm is a Cauchy sequence. Is a Cauchy sequence in R or C. Because here as we read this inequality like this, for a given epsilon by c greater than 0, there exists a natural number n such that for all m comma r greater than or equals to capital N, mod of alpha jm minus alpha gr, that is less than epsilon by c, that is nothing but the definition of the Cauchy sequence, and therefore here we get that sequence alpha jm is a Cauchy sequence. As each alpha jm is a scalar, that means it is either real or complex, and therefore this sequence is a Cauchy sequence in either R or C, and it is true for each fixed j. As it is true for each fixed j, that means for j equals to 1, we get that alpha 1m is a Cauchy sequence in R or C. Is a Cauchy sequence in R or C. In the same way, when we are writing j equals to 2, for j equals to 2, alpha 2m, it is a Cauchy sequence in R or T. In the same way, for j equals to 3, we get that alpha 3m, it is again a Cauchy sequence in R or C, and so on. That is for each fixed j, 1 less than or equals to j less than or equals to n, sequence alpha jm is a Cauchy sequence in R or C. That means here, when we are taking j equals to 1, we get the sequence alpha 1m. That means 1 is fixed, varying is m. That is the sequence alpha 1 1, alpha 1 2 up to so n alpha 1m, and so on. It is a Cauchy sequence in R or C. In the same way, for j equals to 2, we get the sequence alpha 2m. That sequence containing the elements like this: alpha 2 1, alpha 2 2, up to so n alpha 2m, and so on. It is again a Cauchy sequence in R or C, and so on. As these are the Cauchy sequence in R or C, and we know that the set of real number, that is R, as well as the space of complex number, that is C, both are complete. As these are complete, that means every Cauchy sequence in R or C converges in R or C respectively. And therefore here the sequence alpha 1m, it is a Cauchy sequence in R or C, and both are complete. As therefore they are complete, therefore this Cauchy sequence in R or C converges in R or C, and therefore here we say that sequence alpha 1m, that is a Cauchy sequence in R or C, it converges to some alpha 1, which is also the element of either R or C. In the same way, again, this sequence alpha 2m, it is a Cauchy sequence in R or C. As it is a Cauchy sequence in R or C, and we know again R and C both are complete, therefore this Cauchy sequence in R or C, it converges to say alpha 2, which is the element of R or C, and we continue this process. Now, collecting all these limits, we are getting alpha 1, alpha 2 up to so on. We are getting the alpha 1, alpha 2 up to so on. We are getting alpha n. Now, collecting all these limits, we know that alpha 1, alpha 2 up to so on, alpha n, these are nothing but all these elements, and all these elements are either belongs to R or C, and therefore alpha 1, alpha 2 up to so on, alpha n, these are the limits of the Cauchy sequence alpha 1m, alpha 2m, and so on. Collecting all these limits, we are writing y is equals to alpha 1 e1 plus alpha 2 e2 up to so on plus alpha n en. Now this y, that is the linear combination of e1 e2 up to so on en, it is the element of capital Y, and therefore from the sequence alpha jm, we are getting the element y, that is equals to alpha 1 e1 plus alpha 2 e2 up to so on plus alpha n en. Now this is, as it is the linear combination of the base for capital Y, that is e1 e2 up to so on en, and therefore it is the element of capital Y. Now after getting that element of capital Y, now we show that norm of ym minus y, that is less than epsilon. That means we show that ym converges to y, and as here we prove that small y, it is the elements of y. Therefore we have to show that ym converges to y and y is the element of capital Y. That is we have to show for this. Now consider norm of ym minus y. Just putting the value of ym and y, we are writing here norm of summation j is from 1 to n alpha jm into ej minus summation j is from 1 to n alpha j ej. That is equals to norm of summation j is from 1 to n alpha jm minus alpha j, keep it in bracket, into ej. Now here this is less than or equals to summation j is from 1 to n mod of alpha jm minus alpha j into norm of ej. Now here, as we know, as m goes to infinity, alpha jm goes to alpha j for each j, as we prove. For each j, as m goes to infinity, alpha jm goes to alpha j, and this implies that mod of alpha jm minus alpha j, that goes to 0 as m goes to infinity for each j, and therefore using this we get norm of ym minus y, that is less than or equals to summation j is from 1 to n mod of alpha jm minus alpha j into norm of ej, that goes to 0 as m goes to infinity. This implies that norm of ym minus y, that goes to 0 as m goes to infinity. That is, ym converges to y as m goes to infinity. Now we start with that sequence ym. It is a Cauchy sequence. It is a Cauchy sequence in y, and we get that this Cauchy sequence in y converges to the point y, which is the element of capital Y. That means here we get that the sequence ym, that is a Cauchy sequence in y, converges to the element of y. That is sequence ym, Cauchy sequence in y, converges in y. And as sequence ym be any arbitrary Cauchy sequence in y, and for this arbitrary Cauchy sequence in y, we get that this arbitrary Cauchy sequence in y converges in y, it implies that capital Y is complete. Thus, every finite dimensional norm space is complete.